Cek. Ah, tes, tes, tes. Cek, 1, 2, 3. Oke. Selamat siang semua. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon to Pak Stefan, Mr. Stefan. And so I saw here some of the DHI representative in Singapore. Ada Budi Ongkara. Okay, sorry, we are a little bit late.
Hey, good afternoon.
I will talk, yeah. I will talk in bahasa Indonesia just to open this presentation. Terima kasih Bapak Ibu semua. Assalamualaikum warahmatullahi wabarakatuh. Seulang lagi. Jadi siang ini kita akan mendengarkan presentasi dari DHI Indonesia mengenai software mic. Ini merupakan undangan dari PT.DHI, ya, dari DHI Indonesia mengenai perkembangan terbaru di software mic. Pertama-tama saya ucapkan selamat datang kepada perwakilan dari Pusat Hidroceanografi TNI AL. Selamat datang Pak di kantor kami. Dan mungkin dari SCTAL juga ada Pak ya. Oh, ikutin, dan dari perwakilan SCTAL mungkin dari online. Rekan-rekan sekalian dari Pusat Riset Kelautan, di Balai Riset Observasi Laut, di Loka Kementerian Pesisir Bumi, saya melihat juga di sini teman-teman semoga semua dalam keadaan baik-baik dan sehat-sehat semua untuk kita semua. Oke, untuk mempersingkat waktu kita akan memulai presentasi dari DHI Indonesia. So Pak Stefan, I will be your host, your moderator for this presentation. From the letter that we received from you from the HI, that you will presented some of the recent development of mic software, and it will take about 1 hour. So because we are late, about 15 minutes, I hope you still give your presentation in 1 hour, and maybe you will provide some time for us to have some little discussion or some question and answer extra in your presentation. Okay, Pak Stefan, time is yours.
Terima kasih. Hello, everyone, and thanks for the opportunity to present new features and products and tools which we recently developed and which we've developed also over the last years to extend the capabilities of Mic 21 and Mic 3. I would like to share a screen which then shows you the presentation. Can you see the screen which I just shared? This is some blue. Can you see the screen? Okay, I assume that you can see the screen. Otherwise, please let me know. Yeah, here there are some messages in the chat, I guess. Let me see there. Yes, okay, thanks for letting me know. All right, then just let's start. I try to be short so that you get a good overview, but that there will be still some time for questions and comments. So there is a small agenda which I prepared. So first, I would like to give a short overview of the modules which we have in Mic 21 and Mic 3. And then I prepared short sections on each of these modules. I will concentrate on the hydrodynamic module, the mud transport module, the sand transport module, and the ecological models or modules. As you see, we have a lot more, but let's see how time develops, and let's see how far we get to that. But if you remember that we have also waves and ships and literal processes and shoreline morphology, then your questions are welcome on these as well. So let's start with an overview of the Mic modules. So first, why one would turn to Mic 21.3, or why would one like to use it? Because thousands of people try to or use it for over 40 years, and it has a strong history and also advanced modeling features and data processing capabilities and visualization tools. Due to its modular structure, you can compile your models which suit your needs, and that makes it easy to also transform the results into like solutions which you can really apply in your projects. So here is a short overview of the modules which we have recently. So on this slide, you see the hydrodynamic and environmental modules. We have, of course, the HD model, which is the core of Mic, I would say. So this can be used for flow simulations, inland flooding, mud, debris, but also distribution of salt and temperature. And it exists in two versions. In the past, there was only the hydrostatic versions of the shallow water equation, but until now, you also have the non-hydrostatic solution in 3D. So that's a quick approach, or a very efficient approach to do really dynamic three-dimensional modeling, which is faster than CFD, for example. Then we have the advection dispersion and transport module for materials. We have, of course, the Ecolab and oil spill, which is for water quality, eutrophication, heavy metals, individual special entities, for example, oil and fish. And we also have the ABM lab, so the agent-based model lab, which is about the dynamic behavior of aquatic life and the interaction among them and also with the environment. Then we have the particle tracking module, which is for the fate of dissolved, suspended, and sedimented substances. And we also have the sediment transport modules, the mud transport for cohesive materials and morphology, and the sand transport for non-cohesive coarser materials, their transport and morphology feedback on the bathymetry. We also have a lid package, which is for non-cohesive transport along the coastline, and more advanced solution, which is the shoreline morphology, which was developed 5 years ago, I think, or included in the MIC package, which is for long-term shoreline evolution in areas with complex bathymetries. So then we also have the wave modules, the well-known spectral wave module for wind and swell waves in offshore and coastal areas. And then we have the buoy nest wave for short and long period wave disturbance in the surf and swash zone. It can be applied also in ports and harbors because it includes departure reflections on the harbor components. And we have the new Mic 3 Wave FM module, which is a three-dimensional wave modeling package, and it deals with the transformation of waves from deep water up to the structure, right? So also overtopping is resolved in this. We have further the modules for mooring analysis, which is about the motion and the forces of moored ships or other floating structures. So it doesn't have to be ships. It could also be floating wind turbines, for example. And we have, of course, the pre and post-processing toolboxes, which help you setting up and analyze the modeling results and prepare models for wave, tsunamis, cyclones, scour, tidal analysis, and so on. So here is a short schematic sketch of the modules. So you see there is a frame around these modules: the HD, the Ecolab, the mud transport, particle tracking, ABM lab, sand transport, and oil spill. So they are accessible from one user interface, and they can just be clicked and activated to add to the modules. And then we have also these, what you could say, standalone modules, but they can also interact with each other. For example, the Mic 3 Wave FM can feed the mooring analysis module. Same goes for spectral waves and the buoy nest waves. And also the Mic 21 HD, for example, or MAT or sand transport, can work together with the shoreline morphology module and also the wave modules. So I would like to start with an overview of a few of these modules. I watch also the time so that we can look into the things, but not too deep, right? So, but I can extend in case of questions, of course. So this here is just an animation of the Thames estuary in the UK, and that was modeled with a flexible mesh approach. And so here, sediment transport and hydrodynamics are fully coupled so that the sediment motion can affect the bathymetry. And so the bathymetry is updated each time. And the area of applications would be coastal areas, for example, where the dynamic seabed is in motion. And you can also apply or couple that with sediment transport for not only with cohesive, but also non-cohesive sediment transport. So the model can also be coupled with waves. And once it is set up, it can also form the basis for operational purposes. For example, to assess sediment spill or water quality. What we further have is that there is the functionality of simulating jet discharges into the model, right? So if you have outfall or an outlet, you can deal with it, and it is distinguished between a near field solution and a far field solution. So this is done in the model itself, right? But of course it is documented. And in the near field, the solution is determined by complex interaction with the surrounding flow, right? So you have here these leading edge vortices, but also on the lee side, you see here vortices. And in the wake, you have also vortices, and at the bottom, these famous horseshoe vortices. And so this is all resolved in a near field model. But when the jet becomes passive, so when it adapted to the surrounding flow, then it is handed over to the dispersion with the ambient flow approach, so the far field model. And so this can be then applied in all these scales, right? So all these scales are resolved and included in the model. And yeah, so the near field has a big impact on how the plume would later look like, and therefore there is this distinguishing being made. But yeah, that's of course fully documented, but you don't have to care about it, right? You just have to get the input conditions, but these processes, they are included in the solution. And here that is visualized, right? So you have a source location, and then you can develop the the distribution of the plume in the near field. And once this is passive, then it goes into the coarser far field model, and there you can then see how the plume develops. Here, another thing which we integrated, or which we included compared to previous releases, is that you can define bed resistance, especially varying. So this is what you know already, right? So you can have roughness maps, for example, but now it is even easier, because you can just take your output from your GIS data processing. So you can load polygons, so shapes, right, into the model directly, and then if the shapefile has classes like river or grass or park, then you can define Manning numbers for these classes. So there's no need to prepare roughness map based on the mesh or on the grid. This is handled automatically by the model now. And even more, you know that the Manning number is dealing with a bottom friction mainly, and for turbulent situations. But there might be an unsecurity when it comes to different water depths, right? So the Manning number would probably overestimate roughness or the friction losses in shallow areas or with small flow depth. So you can tune these roughness values depth dependent. So you can have a much more accurate result here, because you can give different Manning numbers for different flow depths, and that for each of the roughness classes which you have defined in the shapefile. So that is very nice. And here in this animation, you see an inland application. So there, the houses are also included as shapefile. Here, what you see is rain, and the rain is falling on the roofs, and then it is just flowing on the floor, and it can also penetrate buildings, and then it can be coupled with, for example, urban models, so that it goes into sewer systems or pipe systems. Yeah, and this is so they are not stitched out, these houses, they are included, right? And the water which falls on their roofs, it falls into the model. Then we have easy for improve the downscaling probability or possibility in the models. So if you have a coarse, large model and a fine model in your area, then you can extract vertical boundaries at any location in your coarse model and use that as input conditions for your fine model. So you have 3D boundary conditions actually. And we improved also. It is a small thing, but it is pretty nice, I think. You can have direct output for culverts and weirs and gates. And here I show you, just as an example, how to set that up. So you go to structures, and there you can include a weir. And here in this example, you just activate this output box. Yeah, and then the output directly at the weir are recorded in this file as a time series. And yeah, so in this animation you can see, maybe I show you that in the next slide. Here, that was the model setup. What I just showed you here is the weir, and there is increasing water level on this side of the weir, so it increases, and at some stage the weir would be overflown and water would get into this basin here. And this you can see directly in the output of this weir, because here on the left side, here, this green part, the water level is increasing, and at one threshold here, actually at 0.8 meters roughly, or 1 meter, there the water flows into the basin and gradually increases also there. Right, so this is then a direct output, and you don't have to find your points where to extract time series and stuff, and so this is much easier, and this also works for culverts, right? So you have here now a culvert from this part of the model area to this part, and through this there is just water discharging, and with increasing water level on this end here on the left side, the hydraulic head of course increases, so that the discharge can increase inside the pipe until the maximum capacity is reached. So then we also included a new output function or option for mic 21 and also mic 3. When you know that you have like here various output options, the new one is inundation. So you could have, for example, horizontal or discharge output or area output, and now you can here also select inundation. And what then will be done in the model is it just tracks for you the maximum flow depth, the time at when this flow depth is reached, the same for current speeds, and also the time when a certain water level is reached. So it could be used as an arrival time, for example, in tsunami modeling. Yeah, you just say, okay, I want to capture the moment when a water level is more than, for example, 20 centimeters, right? So then it becomes interesting, for example, in tsunami cases. So then you get this arrival time as an automatic output. Then we have the mat transport module, and here is just one example of how it can work. So imagine a silt curtain, and this is used often to limit the encroachment of dredging induced sediment plumes on, for example, other areas like beaches or habitats. And here you can just test the efficiency of such mitigation measures. Here this is an example of Morocco, where you can see how the silt curtain just reduces the transport into these habitat areas and these beach areas. Why would you use the mud transport module? Well, it is a unique multi-fraction and multi-layer software. The users, they can simulate the erosion, the transport, and the settling and deposition of fine cohesive and of non-cohesive sediments. And this is, for example, applied to dredging studies in ports and coastal engineering. And so they use these models to support critical planning and operational initiatives. So they can investigate the changes in the sedimentation patterns, including the impact of contaminated sediments on the local flora and fauna and ecologically sensitive areas. This is just a good package to investigate these kind of processes. And here you see a sketch of various layers and with different composition, fluid mud, hard mud, soft mud, these kind of things, and all these processes, they are all recorded or represented in the model. We improved also the disposal functionality. So you know that sediment disposal at one source here, for example, that is a multi-scale problem. So there you have highly detailed and complex processes going on in the near field, and then the plume would probably propagate in the far field. So there are several things which going on when the disposal sinks to the bottom, right? So a very low density material, for example, stays longer in the water column, while the heavier material and clumps would just go down pretty quickly. So this is all included, including the bottom collapse phase on the bottom here. And here you can see some photos of our colleagues Jensen and Saremi, and how the plume would look like when it is dumped into the sea. And this is what the model does. It actually represents the stripping of the source. So the density decreases, and the lighter material stays closer to the surface or longer, and it takes longer to sink down. And the heavier material, dense material, goes down more quickly. And then it collapses and generates these surges to the sides. So here on the right side, you see a screenshot of just a snapshot of a model result on the suspended sediment concentrations. Yeah, and this is how you do it. You just select the disposal, and then you have various barges which can have which will have each a disposal plan. So you prepare a proposal plan and can load that here into the model. And the proposal plan looks like this. You have a time plan, so the schedule actually. Then you can define where the barge has to be at these moments, and then how much water or how much sediment is dumped into the sea. You can just type that in here, and also the conditions of the water can be considered due to in terms of salinity and temperature. So that also, if that's different from the ambient temperature, that is also considered. What we also included is a combination of mud and sand transport. So in the sand, you consider the near bed load transport. So the heavier sand, or the coarser sand that just rolls on the floor here. And in the mud transport module, until last year or so, you would have the other process covered, right? Where the fine sand and also the mud is grained out from the soil and goes into suspension, and then is transported away and mobilized by waves and currents. And what we did now is we combined both. So we have a new sand transport mechanism in the MT module, where you can also consider the near bed load transport, and you still have the mud transport, the suspended load sediment transport. And this is important in areas which you can see here, for example, as in a Danish bay, where you have tidal channels which are deep and which consist mainly of sand. And then you have these mud plains where you have like this finer material which would go into suspension, and the coarse material would go into bed load transport. And even if under strong conditions, then it would also go into suspension, of course. Yeah, so this is here and considered in the near bed transport tables, which you can specify similarly like in the ST module, and then you just load that into your setup. And here is a presentation of the results. You have here this bay with the tidal currents. Now the water level is gradually disappearing, just for the sake of showing you or giving you free the view on the bottom. And here, when the flow goes out of the bay, then you have here these orangish colored bed load transport. So yeah, that is just a very recent improvement of the mud transport module. We have also the non-Newtonian flow, which is in the transport module, where you can select mud and debris here, and then you can specify the fluid properties, but they were constant But now, if you also activate the mass transport module, then you can change that property into varying in time and space. And then these empirical functions here, they deal with the mixing of your mud with water, for example. Right? So the conditions of the flow are not the same. They change during the simulation automatically. So then we have this sand transport module where you can look at the shoreline motion in front of the port, yeah, and during seasonal variations here, for example, in the monsoon period, there will come the situation where also sediments can bypass this breakwater here, and then it goes into the port area, and you can here this animation deals with 6 years period, right? So I myself did models which project or which estimate the development of the sea bottom near shore for 40 years. And so this, of course, should go on with the monitoring because it is a difficult task. But yeah, you can do it, and you can monitor and you can adjust. So this is what you can just represent in your model, the siltation here in the port. Yeah, and you would use that just to accurately calculate the transport phenomenon near the coast, and due to wind and also due to waves, due to currents and waves, if you want. I'm just skipping that here a little bit faster. And here you see another animation, how the morphology changed in a channel near a jetty, which is just shown here. And you see that at the beginning, the bathymetry changed quite rapidly in the first 3 months, but later on it gets slower. Yeah, let me be a bit quick here so that we can also reach the environmental modules. Just a short comment. It is the sand transport model is a multi-fraction model. So if you have mixed material on the top, yeah, so under normal conditions, the finer material would be washed out and the coarser material would remain there. So this is, and it shelters the layers which are below them. And these effects, they are also included now in the sand transport module. So the upper layer, until giving the finer material free, it still protects the substrate layer, which is below. Yeah, and it is fed from the substrate layer slowly, but in a sheltered way. Yeah, and the position goes the same way, right? So further it feeds the surface layer. Let's get now to the ecological modeling. So we have this famous Ecolab, and this is just an open equation solver. It works with the ordinary differential equations, so it can, on this logic, it can reproduce effects of chemistry, physics, biology, or ecology. And you can define almost any process on this set of equations which you want to represent in your model. So it is a very generic and portable way to deal with these processes. You can have your own templates, as it's called. So the rules, how these processes are set up, you can tailor them to your needs. We have a big library of templates, but you can make your own and combine them, or use parts of it. And then the model can be coupled with other MIC modules, for example, MIC 21, MIC 3, MIC Hydro, River, for example, MIC Urban in cities, or MIC She, where it comes to infiltration of the body of the terrain. It allows you to really powerful insights into the fate and composition, for example, of nutrients, bacteria, algae, sediments, or pollutants, and all these types of water environments. So you can really investigate the full range of water quality and their potential in the ecological impact. Yeah, and this is an open approach, as I mentioned before. And here is just one example. So there is actually no logical problem which you couldn't capture in the Mike Ecolab. So here is just an example. So in August 2010 there was a triathlon featuring on an open water competition. And wait a second. And so the people, they could just swim, and I couldn't get rid of the noise of the videos, so therefore I just go to the next one. But you could predict with this model how the water quality evolves in a period of time. And when you have a competition running of swimmers, for example, which want clean water, then you can just monitor how the water quality during this event is in the surrounding of the event, and if it is dangerous or not. So that is one application. And here is just another application. Let's see if that is without sound. Yes. So in that case, you have a simulation of a sudden spill of nitrogen heavy substances after a fertilizer factory which exploded in the inner Danish Strait. Yeah, so you can really have the aquatic ecosystem reproduced in a numerical model, and define and investigate any process you would just you can imagine, right? So it's a really open tool for assessing the water quality, and yeah, it's a pretty flexible approach, but you can apply in many situations. For example, aquaculture. Yeah, for example, to understand the impact of changing nutrient outlets on dissolved oxygen concentrations in the water, or to safeguard your livelihood. Yeah, that is just one example. You could, as time is running late, I would maybe pick only one more module, or maybe I just stop here and give you a little bit of time to ask questions on what I presented already, or you could also ask me to present another module, maybe the oil spill module or the ABM lab, just as the time is running out. So please, yeah, get back to me and comment on, and share your comments with me, just as long as we have time in this meeting.
Okay, thank you, Dr. Stefan. So it was a very interesting, very updating information in terms of the development of MIC-DHI. Actually, in our institute, we have some colleagues that already use the MIC software. It's a long time ago, so some of us has already got some maybe experience in using the MIC software, including me. I use MIC software since 2007, so I know. So I'm very happy to notice some of the development. So we saw maybe in the recent version of the MIC, the DHI, I saw some development in the urban models, in the hydraulics also, and in the mud and sand transport as well. So next we will have some discussion or maybe question and answer from the participants about the MIC DHI model. So if any colleagues, if you have some question, maybe in Bahasa Indonesia or in English, just tell me, and maybe you can write in the chat box, in the Zoom chat box, anything. It's a very good opportunity to have interaction with Dr. Stefan, the DHI representation. So silakan Bapak Ibu, jika ada pertanyaan mungkin bisa disampaikan kepada di grup, di chat box, atau silakan, atau bisa berbicara langsung di Zoom. Atau di dalam ruangan silakan, jika Bapak, oke. Dari mungkin pertama dari ruangan yang kita daring dulu Pak, di line. So the first first question is from the hydrographic from the left call Dian from Hydrographic Office in Indonesian Navy. Please let call Dian.
Tes. Assalamualaikum warahmatullahi wabarakatuh. Selamat sore. Good afternoon, Mr. Stevens.
Good
Nice to
afternoon.
meet you and very interesting presentation about this Mac software. I will just combine two languages if I face difficulties about to express my opinion about this. Mr. siapa Pak Agung bisa bantu nanti ya.
Ya silakan Pak.
Juni, from this paper, there is one of the model in underwater acoustic simulator. We are very interesting about this model, and could you please to show us primarily for explain more detail about how the acoustic use in the model. I mean, the propagation of the trajectory or the acoustic source propagate in the water column. If it's available, you can show the result of the model. Thanks.
Okay. Dr. Stefan, please.
I can try to explain a little bit about the underwater acoustic simulator. It was released in 2016, and it just handles in a radial way the noise propagation, and this can be used for AIA related studies, for example, for
Dr. Stefan, can you please slideshow presentation?
Okay. Can you see the slideshow now?
Yes, we can see it. Thank you.
Okay. Okay. Good. Yeah. So this is what is done actually, right, through the water column, and it includes the bathymetry and their effect on the propagation of the noise. So we have at the moment we rely on MATLAB tools to convert like the transects, which are the outputs of the model, to also produce two-dimensional layouts or two-dimensional results, as you can see here on the right side. So we have here all these tools. They are free to download, right? So you have, there is a download page where you can download quite a lot of helpful tools which can be used. And the nice thing about the UIS model is also that you can combine that, for example, with the ABM agent-based modules. That's another tool which I couldn't have the time to present within this meeting. But here, this is just an application of the combination. So you see here how whales move along the coast and travel here northwards. And here you have a source of noise, for example, due to pile driving or oil and gas works. And during these noises, of course, that pushes the whales away. And this ABM model, it just lets you dynamically visualize or track the behavior of the whales, as long as you know how they behave in terms of ways their motion patterns, right, and how they react on things which they don't like. So then you can just reproduce it in the model and see, how the effect would be on the group of species. So that's just what I can say about the acoustic underwater analyzer. If you have more specific questions, then I would have to, then please let us know. and I'll look for an expert which can answer all these detailed questions, if that's okay.
Okay, thank you, Stefan. So the points from this animation is the whales, right?
In that case, yes.
Yes, the points are the whales, and the whales trying to avoid some sound source or some acoustic source, right?
Yes.
Yeah, okay.
But it could be other species as well, right? So you could also describe the behavior of yeah, any species, yeah, with a noise.
Oke, terima kasih. Apakah ada pertanyaan lagi dari rekan-rekan sekalian? Silakan dari di ruangan yang online dulu, mungkin ada lagi. Oke, sekarang dari ini dulu, dari chat belakangan kali, dari ini dulu, dari online. Yang silakan kalau ada yang mau bicara, maksud saya. Ada yang mau angkat tangan mungkin untuk raise hand, silakan. Kalau ada yang mau ngomong langsung sebelum ke chat box. Silakan, ada tombol raise hand kalau mau ngomong, bicara, bertanya langsung. Oke, sekarang kita langsung ke chat box. So we continue to the chat box, Dr. Stefan. We have some questions here from our colleagues. So the first question is in Bahasa Indonesia from our colleagues Humus Padang. To translate to you, is there any books that is really sold for its module in the SI in mic software?
Yes.
Yeah, is it in Bahasa Indonesia or in English, or is it all the books can be downloaded from the software, or if we install the software, or like what? Thank you.
Yes, I show you a way to access all the documentation of the model. I would again. Oh, you can still see my screen. Can you still see my screen?
Yes, we can see it.
Okay. So I click here on start, and then I just start typing mic 0 documentation index. So I just start writing here, and then you just click on it, and I just have to get it from the other screen, and then you see here the entire documentation. So you have here the latest release notes, but when you look for a module, for example, in mic 3, you just click here, and then you see here all the books or the PDFs. Is actually, you can also print them, of course, but you see here, this is the internet page, yeah, with these 2 slashes here before the year, and you can just select what you want. So you have for the Ecolab, for example, you have a user guide, you have a step-by-step training guide, you have step-by-step training guide for ABM example. Then you also have Ecolab, Mike Ecolab user guide, which allows you to do the templates, to develop own templates and adjust existing templates, and also the same, and you have scientific documentation, for example, for oil spill models and data sheets and things like that. And that exists in some way for also the mud transport module, the user guide and the scientific documentation, and also for the sand transport and the particle tracking and the wave modules and the integrated modules, underwater acoustic simulator as well, user guide, scientific documentation. So that's pretty comprehensive documentation, I must say. So yeah, if you don't find the information, then of course you can ask, but I'm pretty sure you find everything you need to develop a model or to learn more how to apply the model. Right? So you have here really a set of examples which guide you through the process of setting up your model. These are in English on this page here in my installation. Maybe Aseb, do you know if there's if there are some material also in Bahasa? Ohan, yeah, I don't know if there is existing information in Bahasa. Some probably, maybe not everything.
Okay, thank you. Answer. So we continue to another question. Next question is from Mr. Arif. Can you read the chat box from Arif S?
Okay.
About the effect of the mangrove in the coastal erosion. You can see you can read the question. Can you get the point?
Mm-hmm. All right. I just read it loud so that the entire audience can also know what the question is about. As we know that northern coast of Java are having heavy abrasion issues, mangrove as a vegetation could be green solution for that problem. Is there any way Mike 21 can model mangrove forest and its probable sedimentation, and also compare it if there is no vegetation on the coastline, and also its effect to reduce wave attack on the coastline? Shallow water modeling are sometimes inaccurate. I fully understand the problem which you're facing in the tropics with where mangrove forest is to stabilize coasts actually, and this should be considered in an numerical model. What we can say right now is that we don't have a specific mangrove solution, but you can include structures, for example, in your model cells, and there you can give drag resistance factors. So if you have a scientific paper where you know the drag coefficients for mangroves, I know that there is some work done also in Indonesia on this topic. So you could include that in the drag equation. Let me see if I can find a setup which could maybe help with that. I just open any setup, right? It is not fitted for this purpose, but I just want to show you where you can go. You can use the peers function, right? So you just add peers, and then you can go to this, and you can give a height and the width, and you can have a position. Of course, that would be done for each of the plant actually, right? So that's a bit but you have to do that once, right? And then you can reproduce this section in the text editor and add that to the model. We could probably help you with showing you how this is most efficiently be done, and then run the calculation. So this is a solution which we could propose just right now, right? So you can here specify the shape of your structure, and mangrove would be circular, the root structure, right? So there are circular roots, and then you can adjust here the streamline factor to consider this drag loss in your simulation. Yeah, but to apply this method, you would probably have or like to have some measurements or a laboratory test case where you can tune your model, right, so that it reproduces. So you should validate this approach. Yeah, this is what is implemented right now, but we know there is a topic, and we are certainly thinking about improving this.
Okay, thank you for your answer. So, is there any questions from my colleagues
question,
here?
please.
Yeah, Pak Johan.
Yeah. Hi,
Okay,
Stephen.
please.
My name is Johan. I'm from Marine Research Center. Anyway, very interesting presentation. Just want to check if the mic tree, since I read the leaflet that it includes Run's equation, Reynolds average never stops. And then it's very interesting if to have two wave resolving model, phase resolving models, which is Bosnian and a non-hydrostatic model into in one software. Have you ever compare both of the model, which one is more accurate? And yeah, just interesting. What do the non-hydrostatic model can do in Mach 21 or Mach 3?
Mach 3, yes.
Yeah, yeah.
I can also open Mach 3 setup. Here just you go to Mach 3 and then you open, for example, the wave or the flow model, and here you can select in the hydrodynamic the basic equation, right? So it could be the shallow water equation, which would be the hydrostatic approach.
I cannot see the slide. Please, I don't know whether.
Oh, I see. I have to share the screen again.
Yes, please.
Okay. So what I just did is I opened a brand new setup, the flow model here for Mach 3, and there you can.
Stephen, I cannot see the slide.
Oh, okay.
Cool.
Now it is. So this is the Mach 3 model, and in the hydrodynamic section, yeah, you can here select or activate the models you want. But here in the basic equation of the hydrodynamic model, you can switch between the shallow water equation, which would be the hydrostatic approach, or you can also switch to the Navier-Stokes equation, which would be the non-hydrostatic approach. And yeah, so the model looks just the same, just as the set of equation in the background is different.
I see. Yeah, cool.
So it's very easy compared to CFD models, right? So you have the user interface, which you're familiar with, and it's very easy to set up such models, right? There's almost no difference if you want to use the hydrostatic or the non-hydrostatic approach.
Yeah.
You just switch, right?
Can we also get output like, for example, what's the name, water level over time within the boundary, for example, and then later on we can translate it into wave like we usually do in Bosnia's model. Is it possible in Run's equation in Mach 3, or we have to switch into wave module in Mach 3?
You think you
Since sometimes I am sorry, I have some experience with pressure solving like swash and X-pitch, which is, I don't know, is it also the same in Mach 3? The approach, since in both of models, like the swash and X-pitch runs with non-hydrostatic approach.
Yeah.
And then is it the same in Mach 3? The approach that you use in this equation?
Yeah, it is pretty comparable, I would say.
Okay.
With regard to the state variables, as you refer to the Boussinesq wave model, which I understand from your question, these phase averaged results, like a significant wave height, for example, or so the state descriptions, they are only produced in the Boussinesq
I see. Okay, cool.
This here is pure phase resolving module.
Yeah. Thanks a lot, Stephen. Yeah. Thank you, Pak Yoga.
Okay, thank you,
Yeah.
Pak Johan and Pak Stephen. Maybe I will open one more question from the participants online. If you have any question, just you can use the raise hand buttons or just talk. Okay, no more question from. No. Okay, Ulung, Pak Ulung, please.
Okay. Hi, Stephen. Very interesting presentation about mic software. First of all, I used to use this application and this software for generating like a flow model in the past, but now I'm in the running of taking a master in Japan, and I plan to make a model for a tidal wave in an estuary. So if I consider using the mic software, could you give me a suggestion which model I can use to model the tidal wave in the estuary area, and to make a simulation about the evolution in the estuary?
Yeah.
Maybe, yep.
I think you could probably use the mic 3 non-hydrostatic approach to see also you want to see the wave, is it?
Yes,
you want
correct.
to see how the tidal wave in an inlet
yes.
jumps up. Okay. Yeah. I think one way would be to use the non-hydrostatic HD model. We did a study on a similar kind of phenomenon in Bristol in the UK. I remember that. For ensuring the recommendation to you, I would talk to the guys who did the study and get back to you by email. And so they could probably point to some issues which they run in one model or another, so that we can that you can choose the model, right? So I would like to. Another way would, of course, be to use the mic 3 wave FM. But I need to talk to the guys which are the advantages, disadvantages, and would like to send you this list of advantages, disadvantages of the model.
Okay, thank you, Stephen.
Okay, thank you. Maybe one more question from online. If not, if there's no more question, maybe I will ask some questions from me. Stefan. Okay, I have one questions about the baroclinicity in the model. So I haven't seen any in your presentation. I haven't seen any sample or test case in Indonesian seas about the baroclinicity. So if we force the model in the three-dimensional from the mic 3, I saw from the internet that we can give some forcing in the output in the boundary. Just download, for example, from the global model, the ICOM or any other models. The question is, if we including the baroclinic in our 3D models, or especially in the Indonesian region that is very large, and we must take into account the layer from the surface to the bottom. It will take about more than 20 layers. So the computational cost, it will be very, very expensive. So is it possible for mic 3 to run in the Linux environments or in the HPC computer systems?
Yes.
Yeah, thank you.
Yes, you can do that. I also have a slide here on this. So you have various options, right? You can run the model on the Azure Marketplace, the Microsoft Cloud Computing. That would be one option. And of course, you can also So yeah, you can also use supercomputers. So even on Windows or on Linux platforms.
Okay, thank you. It's very interesting. So I think there's no more questions. So maybe we can end this presentation.
One more comment, please. You can also use GPUs, right?
GPUs. So
yeah.
Okay.
So I have
cheaper
here
than CPU.
Yeah, I can show you here a benchmark case which we have. This here is the speed up, right? If you use one CPU or 12 CPUs on various measures, right? So these are all 3D cases, and we tested just measures up to 13 million, right? And then you can see here the speed up factor if you use various Tesla GPU cards. So you can get an increase of like up more than 100, right? So it is incredibly fast, and this is for double precision calculations. So in the planning before the production run, right, you can also have like simple lower order schemes, yeah, and they are approximately 50% faster even.
Okay, that's very modern capabilities, and yeah, very up to date. Okay, thank you. So maybe we have maybe we can end the presentations. I would like to say thank you to everyone, to my colleagues in Marine Research Centers, to our colleagues in Padang, in Japan. So thank you also for the DHI representation, Dr. Stefan, Madam T. Ong Tan, and okay, okay. Okay, thank you for everybody, and we can end the presentation. Thank you. Have a nice day and keep healthy to everyone. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Thank you. Thank you. Bye-bye.
Bye.
Thank you. Bye-bye.